Okay. We will get straight on with things. So, to those of you who are new to Devon Moth Group, because I know we have advertised this meeting a little bit wider than just the Devon Moth Group membership. So, if you're here from Devon Bat Group or from Butterfly Conservation or from anywhere else for that matter, welcome. My name is Richard Fox. I'm chair of Devon Moth Group, and we'll be chairing this meeting tonight. But you don't want to hear from me, really. The reason why you're here is to hear from our distinguished guest speaker tonight, Professor Marc Holderied from Bristol University. Marc's primarily interested in sound and how a wide range of different animals use sound to navigate the world, to communicate with each other, and to find resources. He's also, I don't know whether he's going to talk about this, but he's also interested, I know, in how the approaches that creatures have evolved can also be used to benefit us humans through the design of new materials and engineering. But I will leave it at that point and hand you over to Marc. Thanks very much for joining us and giving up your time this evening, Marc.
Thank you, Richard, for this very kind introduction. Can you all hear me all right?
Yeah, that's great.
Okay, cool. Well, it's a pleasure to be here, and it's a great turnout. So looking forward to hopefully give you some inspiring stories over the next 45, 50 minutes. Those of you that might have seen previous talks, I hope I'm not telling you stuff that you already know. I will give you my 3 favorite stories tonight. That will include the latest update on all of those. I don't know how much you're on social media, but I'm so proud. I simply have to tell you. So yesterday we had a social media superstar here on campus, and I happened to be filmed by him. So there is this guy called Max Klimenko, and he has a series called the Career Ladder, and you can take that literal. So he stands on one side of a little ladder and I stand on the other, and this is how he interviews you. It turns out that he is absolutely super famous TikTok content creator of the year. He has billions of views, and he didn't even tell me that he was live streaming what we were doing. So I'm actually quite shocked in hindsight. So if you're on social media and want to look for Max Klimenko, you can get a bit more about what I'm interested in. Okay, cool. So what I'll do is I'll start sharing my screen, if that's okay with everybody.
That's great. Thank you. Yeah, that looks great.
Okay, good. So we're ready. So today the title today is Wingtip Decoys and Stealth Cloaks. I will be talking more broadly about the very amazing acoustic defenses that moths have against echolocating bats. I started out as a bat researcher. Well, very initially, I worked with orthopterans, the acoustics of grasshoppers. But then I did my PhD on bats and a lot of stuff. And I came here to Bristol as a bat researcher. But now I'm firmly in team bat food, which of course is nocturnal insects. And this is because I believe they have the most amazing stories to tell. And I hope that I'll show you some of the amazing pages that evolution has written in the book of this acoustic arms race. Okay, let's see. Cool. So I've got loads of people that have helped contributing to the stories I'll be talking about tonight. And here are the most important ones. David Agassiz might be the most familiar face on this slide. And he has been a good friend and collaborator for many years now. So I've talked about that already. It's the bats and how they try to catch the moth and the bot. And then the moth's defenses that help it avoid being the moth's next meal is what really fascinates me. Here is a picture from an orchard in the Middle East. In a group like this, you probably immediately worked out what this is. This is not spiders. This is lepidopterans. These are the larvae. These are communal webs of these little critters here, and when you hatch them, they look like this. So this is a Microlepidopteran from the genus Ipponomuta. Of course, David Agassiz was at the starting point of this project, given that this is well, sort of his genus, where he's done a lot of the work on that particular genus, but in Microlepidoptera in particular. So it started when he described an odd structure in the wing and speculated, and then we had a PhD student together and then another PhD student. So I'll give you a short summary of quite a lot of research. And at the center of this research is this video here. Can you hear the sound? So this is already slowed down 25 times. This is on a tether. And when you hear, there are clicks produced, trains of clicks, whenever the wing rotates. So this sound, we can hear it now because we've slowed it down so much, but it actually is not audible. So we only found out about it when we had a bat detector next to it. And I'll talk a bit about moths and bat detectors in one of my future slides, because I've got a bit of a tiny hidden agenda here. Okay, so this is the structure that David Agassiz identified. It's at the base of the hindwing, and it's translucent, and it's actually an identifying species for this whole family. And if you look closer on that structure, you can see that it's denuded of scales, hence being translucent. There is a clear window that I'm circling now. Can you see my cursor all right? You can see the clear window, and then next to it you see a series of ridges. So it looks like there is a strong structural modification in that area, and I'll tell you how we managed to make sense of this. So the first thing we did is we did a 3D scan with some nanoscale X-ray to get some structural detail, and this is the region. The yellow line is the cross-section that you're seeing here, and it cuts across the main veins here, the cubital 1 and the cubital 2, between which this is spun out. And then you can see that there is some modification. It's not a constant thickness wing. And the transition point between the striated area and the clear window next to it is particularly elastic. So we've got some other studies, maybe I have it on the future slide, where we can show that in this area there's an elastic area. And we've assumed that by rotating that wing, that elastic area might allow this region here to snap through. I've got an animation here. So this is something where we applied some forces and did some mechanical modeling with a mechanical engineer on the material properties of insect cuticle and on the aerodynamic forces that we think. So this is what we think happens in real life when this wing rotates at the top and at the bottom of a wing beat cycle. We have some imaging here where we see the wing structure in the original state and then in the snapped through state. So you can see that the relationship between the clear window here and the striated area next to it is different. So you can see that there is a movement of a couple hundred micrometers, which as far as sound goes is massive. So there's a lot of air displaced, and it means there's a lot of sound potentially produced on this. I can't show you it snapping through in real time because it's only like a millimeter long, and there is no imaging apparatus that allows us to do this. So you have to take my word for it that it really happens that way. So when it snaps through, it doesn't snap through in one go. Actually, each of these ridges here has a different elasticity and a different resistance to torsional forces. So they snap through in sequence, one after the other. And each of these snap throughs creates one of these clicks. So when you heard the flying moth just now, each burst of clicks is the number of clicks corresponds to the number of these little striations. We call them microtymbals, and they snap through individually in sequence. And you might have heard that there is a change in pitch as well. So it, and that is the tuning of the whole structure, which gives it its amplitude and also a frequency component. And that's the next slide. So here, now we've used a machine called a laser Doppler vibrometer, which can pick up these tiny vibrations of the clear area. So that's the clear area here and the striated area right next to it. And the clear area acts as an amplifier, while the striations act like, well, you can think of this like a drum, and you have the drumsticks, and you hit the drum at the edge, and then sets the drum into motion, and that creates the sound that it produces. And as more and more of these snap through, they just slightly change the tension in that drum, in that clear window, and that tunes its frequency response. And we could find different vibrational modes that are determined by the mass, the elasticity, and the shape of this. And we can relate the peaks in the spectrum. This is a recorded frequency analysis of the click. We can relate the frequencies of these resonance modes to the peaks in the sounds that are emitted. So we think we have a fairly good understanding now how the sound is produced on this. So it's a snap-through burst, so it buckles through in one direction and then it buckles back in the opposite direction at the opposite end of the wing beat cycle. Okay, now I've told you all about this amazing research into how the sound is produced, but what's the ecology? Why do they do this? And of course, it's to do with bats. And when we're talking about moths producing sound in defense against bats, the first everyone here would be thinking about is the tiger moth. So here's a North American genus called Cycnia. That's a typical example. And we know what the timbal, the sound-producing organ of the tiger moth looks like, and that's it. Anything look familiar? So you can see a clear area here, and right next to it, you can see this area of striations. Up here, for comparison, is the aerial elastic timbal on the Ipponomuta. But keep in mind, the top one, the Ipponomuta, has this structure on the wing, and it's operated by torsional forces during the wing beat cycle, while the tiger moth have it at the side of their thorax. So it's the extra, it's the cuticle on the outer surface of the body, backed by a tracheal air sac on the inside, and it's operated by a muscle that's under a neuronal control. And the other thing that the tiger moths do differently is they have ears. Ipponomuta and all the other species we found in that group are completely deaf. So Cycnia only produces sound when it hears an approaching bat, while Ipponomuta is deaf. So the only choice it has is to produce the sound whenever it's at risk, and that's whenever it flies. So evolution has found a really cool way to produce sounds whenever you're at risk. When you're sitting, you don't want to give away where you are, but when you're in flight, the protection is on. So what we have here is an example of convergent evolution. Let me play the sounds, slow it down, so you can compare how similar they actually sound. That was Cycnia, and that's Ipponomuta. So very similar in rhythm, in patterning, in structure, also in frequencies. So we say that these are acoustically mimicking each other. And because both the tiger moth and the Ipponomuta have toxic compounds in their body, they are considered proper Müllerian mimics. So they all contribute to educating the bats. And the benefit of producing the same sounds has given them this convergent structure. So evolution is just such a great inventor. So you produce click production in the wing, and then just by evolutionary processes, you end up with these extremely similar structures. We've looked at the click rate, we looked at the density of these, and we could confirm that this type of signal traditionally is an aposematic signal, so a warning signal. Other species with slightly different signals have jamming signals, so they just blast the bat the last moment, and it overloads their echolocation system. So it creates lots of false echoes and that protects the real echo in this blur of fake echoes, and that's how they protect themselves. So that's the general ecology. There is one more point I want to make, and that relates to this directional plot here. If I'm in flight and I produce clicking sounds, I might actually increase the risk of attack by attracting more bats that are just listening for the noises that I make, in particular naive bats, or a bat species that over evolutionary timescales builds up a tolerance to the toxic compounds in my body. And so that's a perceptual conundrum. So how do I protect myself without increasing my risk of predation? And acoustics allows us to see whether that actually is a real risk. So what you have here, the white line, is the average echo amplitude that we measured for this moth as a function of direction. So in front, the echo is actually very weak. And the side, there's a strong echo. And then from the back, it's also a bit weaker. And the green dots here are the amplitudes of the clicks. And I've not plotted the actual amplitudes. I've translated this into the calculated detection distance, either by echolocation or by listening for these clicks. And look how beautifully the green dots, the clicks, are not louder, are not more perceptible than the echo. So in a sense, the clicking is only audible to the bat at the very moment that it hears the echo anyway. So you're not increasing your predation risk at all. This is such a beautifully tuned system. And another example how evolution creates the most amazing adaptations that we are completely unaware of because we are not participating in that ultrasonic arms race. Okay, so here back to our elastic timbal. Now you know exactly how it works. But it's not the only aeroelastic timbal. If we look at Microlepidoptera, we found that this cell here, which is just on the subdiscal on the hind ring, is only one of 4 regions in which we find aeroelastic timbals. By the way, they're always associated to these predefined creases or fold lines in the wing of the Lepidoptera. So here, that's the CF here, and we've got 2 more here. So we've got the same area in the forewing in some species producing these. We've got the tip of the discal cell. Clearly, there's a lot of deformation and energy during a wing beat cycle in that region. And then we've got a cell in the subcostal or below the subcostal region, which also has this. So what we've done and published a few years ago now, we've done a phylogenetic analysis. But what we only can do is we can only look for structures we think are candidates for sound production. And this is a Microlepidopteran phylogeny that we chose for this. And you can see that in quite a few of the superfamilies do we find examples of this. Tineids are particularly productive. In there, we've got all 4 regions in certain genera. We've got in the Hyponomutids, we can see those, but you can see the Theobatra, another genus in that subfamily, has it in a different region of the wing. You can see if you do the color code, there's actually quite a few of those where we know that there are candidate structures. There are a lot of UK species that we have never had in front of a microphone while they were alive. You can see I've got 1, 2, 3, 4, 5 recordings in total of all of these. So here's the call to arms for all these mothers out there that have a bit of a knack for microleps. I want you to encourage you to open your ears to moth sounds. My aim is to get sound recordings of all UK species. For that, I've teamed up with the British Trust for Ornithology. So they do acoustic classifiers. And we've done one study with one of their large data set from Switzerland, where I gave them 1 or 2 recordings of Hyponomuta, and they popped up everywhere as bycatch in their bat recordings. So we can use this to monitor certain subsets of Lepidopteran species, and we are just scratching the surface there. There is real discovery waiting. There are species out there flying around every night that produce sound, but nobody has ever recorded them. So if you happen to have a bat detector, some moth people are also bat people, set it to 30 kilohertz and put it up next to your light trap. And then when they flutter by, you should hear these very noisy, typical rasping, not anything like a bat, much more rapid and very rasping. So it's very easy to recognize. What's not so easy is then finding out which of the many insects you have at your sheet actually produced it. But if you do manage to confirm the species, that's amazing. Ideally, we would like to get some recordings of those. So collect them, reach out and send them to Bristol, and we can take the recording. It only takes a few moments. But here in the Bristol Moth Group, I currently have a handful of recording microphones that they have to use with their moth catches. And they keep sending me recordings of moths. And yeah, we are trying to build on that database. So far, no real winner, nothing new. But I know that there's several species out there that we need to do. If you've got people that collect bat that visit or count bat roosts in bat droppings, there's a good number of tinnates that are there that we haven't recorded. So that's another way in which we could find new species for recordings. So if any of you is particularly interested in this, reach out and we can talk about how you can get involved in this. Okay, so let's go from some microlabs to some truly macrolabs next. This is by some measure the largest Lepidopteran species that we have on the planet, the Atlas, Southeast Asian tropical. It's very popular with breeders, which is why we have access to them and we study them quite a bit. And it has this truly exceptional wing shape. So this four-wing wingtip has this odd lobe. And we have done a lot of research into this lobe over the years. Let me tell you why. So our starting point is that this wingtip often is likened to a snake's head. I think it looks a bit like a snake head. I even think that the line down here is the snake's body. You can see counter shading. You can see some scales on the belly of the snake. And when they sit, they move their forewing and their hind wing next to each other. So it looks like the snake is undulating or slithering up the tray that they're sitting on. So I believe this is a classifier. But does another organism also think this might be a reptile? So what I did is I asked one of our AI friends. So I asked Bing Photo Search to tell me what it thinks it is. And of course, the first hits were the right thing. But then there were quite a few hits of reptiles, lizards, in particularly skinks, which I found intriguing. But this is Bing's perception. But if a skink, or if Bing thinks that this is a reptile, why shouldn't a bird brain think that this is a reptile and offer it some sort of protection by startling it, by mimicking a predator? So that's the visual camouflage, quite stunning. And if you are into silk moths, and you can look at quite a few species, some of them even have two eye spots on here, and it looks like a little head that looks in your direction. Actually quite a cute face. I should add that as a picture to my slide show. I don't have one today with you. So we can assume that this is a visual one. But there are quite a few saturniids that have these odd wingtips that don't have a fake snake head on it. So they miss all the other parts. No eye, no mouth. But they've got one other thing in common, these lobes. I don't know. Usually in an audience, I would ask whether you can spot what's different here. Maybe in an audience like this, to save you from unmuting yourself, I'll just say it. So if you look at the wingtip, you can notice that the wing doesn't look like it's fully extended at the very tip. See that? It looks like there's some excess wing membrane between the veins. And you can see that consistently in all of them. And that is what piqued our interest. And we believe this is something quite remarkable. And over the next few minutes, I'll try and convince you about our interpretation of this. We believe this is an acoustic decoy. So fighter planes that are under attack by radar-guided missiles often deploy these decoys, which have a very strong radar signature and attract the attention of the attacking rocket, thereby protecting the body. We wanted to see whether in the silk moth, these wingtip lobes can act as decoys. And for background, I made this discovery and some colleagues in the US confirmed it. These hindwing extensions that you also find in silk moth with these weird contorted shapes have been shown to have these acoustic decoy functionality. But now we are looking at the far less contorted wingtip. But if you look close enough, you can see these ripples. And you can also see some interesting folds. If you do a bit of analysis, you see that there are regions of the wing membrane that meet at 90-degree angles. And that will become relevant in a few moments. So first thing we did is we got us a good number of Saturnid species. By the way, we study them because they're beautiful, they're large, and they're completely deaf, which means we suspect that they have different defense mechanisms. And most of them are not toxic, so they're really perfect bat food. So if we took a medium to small sized Saturniids and take acoustic measurements, here that's a frequency axis here, that's all the frequencies that bats might be using. Then we can measure in the upper plot. If you go to the left, you can see that's the target strength. That's actually the target strength difference between the body, that's the part of the moth that you want to protect, and the wingtip, that's your decoy. And here you've got this horizontal line. If you're below the horizontal line, that means your body echo is louder than your wing echo. And that means you attract a lot of attacks to the body and have little protection. You want that curve to be up there above the horizontal line. Here you can see a different way to plot this. This is the decoy-win proportion. What's that? If we compare the two echoes for many different directions, I usually measure 5,000 echo directions for every specimen. So if we do that, then we can for each direction calculate whether the body or the wing is louder. And you can see that everything here, again, is below the horizontal line. In other words, these unmodified, simple, smaller ones have no protection to expect from their wingtip. But when we look at the other groups, the ones that have only ripples, or the ones that have ripples plus these folds that I showed you in the first slide, you can see that the curves move up. In the ripples only, you get to the 50-50 rate. So that means that every second attack should go to the wing. And if you also add the folds to it, you can see that there's up to 90% win rate. So that means only 1 in 10 attacks, in this case, would go to the body. And we can compare this to some behavioral studies, and it really gets together rather nicely. Look at how powerful protection this tiny modification, just give a bit of excess wing membrane and let it fold in a specific manner, gives them. Really cool acoustic engineering. And for comparison, this is the known decoy of the hindwing, and it also achieves the 50% attack rate, not better. Even so, it is the most studied and most well-established decoy that we have at the moment. So wingtips are decoys, but how exactly does this work? We published that now 5 years ago. If we do a cross-section through that wingtip, you can see that it has a very regular shape. And if you do a bit of a mathematical interpolation, you see that these are not sinusoidals. They're actually hemispherical shapes. And this is just one axis. In the other axis, you can see that there's like a bit of an ovoid. And if you have a hemispherical one, something remarkable can happen, and that's double reflection. So the sound enters, is reflected from one wall at 90 degrees angle, hits the opposite side, is reflected again at 90 degrees angle, and that means it's 180. So that means that sound, that ray of sound, is reflected straight back to where it came from. So just by giving this hemispheric shape, you're turning this into what we call a retroreflector, the acoustic equivalent of these cat's eyes that you might be familiar with from bikes or from joggers. So it really is a simple trick. Give it the right geometry and it will produce a lot of reflection. And the folds that we have also seen that are even more effective, they do the same thing with this 90-degree angle. Again, they do double reflection. They are not as omnidirectional as the hemispherical ones, but they are very effective and produce a lot of the echo overall. So we can see that if you don't have a decoy, basically you are bad food. If you've got a hindwing decoy, you've got a 50-50 chance. But if you've got a really cool, well-developed forewing, you can have up to a 90% survival chance just by this tiny modification. Beautiful biological engineering. This is a little machine we built, not so little. It's an acoustic tomograph where we send ultrasound and then use an acoustic camera for ultrasound to see where the echo is coming from. And this is direct confirmation that the strongest echo is coming from that wingtip. I'm trying to build a real-time imager, and I've asked the EU to give me a lot of money to do this. So in 2 weeks' time, I'll be interviewed. So let's hope that they see the light, and we'll have an acoustic camera that shows us what a bat's world of an object looks like. But for now, this is the best we have. And here's another phylogenetic tree, which tells us where these decoys are found within the Saturniids. We can see in gray or black those that don't have a modification, in blue those that have ripples, in red folds and ripples, and in green the hindwing decoys. You can see that it's very common within the Saturniids. It's not all species, but it's a representative coverage. And you can see that, for example, the green has evolved a number of times independently. So has the blue, maybe not so much the red. But you can see that there seems to be a very productive playground for acquisition and loss of these defenses. Interestingly, you only ever have one defense. You either have a forewing or you have a hindwing. Having said that, there is one exception, and that's the Hercules moth in Australia, where one sex has it in the forewing and the other sex has it in the hindwing. Beautiful. So it's the exception that confirms the rule. Why do we believe that they're not doing both? I think it might be energetic. There must be aerodynamic costs for carrying these structures, in particular for the hindwing decoys. But I also believe it might have a perceptual reason. So if you've got 4 echoes, one from each wingtip, and you integrate that, well, the center of gravity is where? At the body. So you might produce a deception that is completely counterproductive because it brings the attacker exactly where you don't want it, back to the center of the body. So that's the story about the decoys. And the final story today is about the rest of the wing. A decoy produces a strong echo, but it's more efficient if the rest of the body is producing less and less echo. So we are looking here at acoustic stealth camouflage. So how can you become acoustically invisible? And if you look at a moth, the body is usually very furry, much furrier than that of a butterfly. So here is an apparatus, the acoustic tomograph. This is what we use to take moth echoes. And we can use this to reconstruct an acoustic image of the moth. Here are some examples. So let's look at this one first. These are 2 different ways to show this. You can see that the body is actually not very strong. There are structures on the wing that produce a strong echo. You can see that there's a wingtip decoy, which has a strong echo at the tips. And these things here, they are just mounting artifacts, because in that dried specimen, the hindwing has a fold in it, which in flight would be flattened out. So that is ignore these strong echoes. So clearly the decoys are the strongest. But what we then did, and I had a team member called Thomas Neal, and he was the world expert in shaving moths. So he removed all the hair from the body, and then we took the image again. And what you can see is that the body all of a sudden lights up very brightly. So that's direct confirmation that the fur on the body of a moth is a sound absorber. We did this more systematically. Here again, this is again target strength. Red is when it's shaved. So you can see the echo is much louder than in yellow when it is completely intact. The blue line in the middle is when we only clipped the epaulettes that are covering the wing joints, but that's a different story. And if we do this in two different moths from two different families, we see a similar effect. If we do it in two butterflies, we see no effect, if not the reverse one. And down here, we have calculated something that we call the protective value that they gain by this fur. So we look at, think of this as a detectability sphere or bubble surrounding a moth. If a bat is inside the bubble, it detects the moth, it gets the echo. If the bat is outside, it doesn't. So here we have measured for each frequency by how much the body fur shrinks this bubble of detectability in percentage of volume. And what we can see is the orange curve is the relevant one here. We see a 40% reduction in that volume. So that's a 40% reduction in the risk of being detected by a bat just accidentally flying within your bubble of detectability. It's remarkable that it's the same for all frequencies. That's not trivial to achieve. And we can see a similar pattern in this different moth species, not quite as good, but still at or above 30. If you look at butterflies, very little, sometimes even the inverse in fact. So the scales make it more detectable, reflect more sound. Very interesting. Again, we published that 6 years ago now. How does it work? It's the furriness, of course. You can see the hairs are longer and thinner. This is the insertion point density in the cuticle. You couldn't fit more hair in here. If you compare that to the butterflies, you can see there is a lot of empty space. Some of the scales are not even modified. They look like standard wing scales. They're shorter, they're sparser. So clearly there are some structural differences between the two. And this is a full scan of a thorax with the half of the thorax chopped away. And this is the tufts of hair of the fur here. We use this to measure the thickness of the fur layer and find out how ordered it is. And down here you can see an insert of a single hair. Even they have really cool structures. They're nanostructures, they're hollow. And we use that sort of analysis to compare it to sound absorbers that we use in architectural sound absorption. So fibrous absorbers, look at this. This is a technical sound absorber you can purchase to make your lives a bit quieter. Look at how similar they are. Similar volume ratios, similar orientation. So fibrous structures are in there, fibrous sound absorbers. The other type of sound absorbers look more like this, and they're porous sound absorbers, and that's what we see on the inside. When we compared the performance of the moth to the performance of these, we found that evolution is as good as our engineers, but only marginally better at some frequencies. So to me, this shows that these sound absorbers, the fibrous and the porous sound absorbers, are a mature technology. We have been using them for 200 years. So we've found the optimum. We can't improve them anymore. Okay? That makes it less interesting for me to study if I want to learn something new. But let's look back at our initial moth. If we look at the wings, they also have to be protected. Think about a fighter plane that has stealth coating only on the nacelle, but not on the wings. Of course, enemy radar would immediately pick up the echoes of the wings, the radar reflection of the wings. The same applies here. If you want to have protection for your moth, you need to protect the whole body. That means, in addition to effective furry sound absorbers, they have to have equally powerful sound absorbers on the wings. Now, thinking about a moth that has fur on the wings on both sides, like a 3-4 millimeter thick wing, it's intuitively clear that this won't be an organism that can fly. It's too heavy, it's too flimsy. It would be a very sad creature to look at. So evolution had a challenge here. And the challenge is to play with what it has on these scales. And these are these wing scales, these tiny structures, highly modified, fascinating structures. So many interesting things happening there. So what we did is we put our moth shaver and again measured, but now on the wing, the acoustic effect of the surface coating. And this is the most important slide, I'd say, of today's lecture. So let's give us some time. So this is a frequency axis. So low frequencies here on the left, high frequencies on the right. It's again the ultrasonic frequency range we've seen. I've plotted something slightly different here, which will become important a bit later. And again, we've got a horizontal line, and that separates positive absorption coefficients from negative absorption coefficients. So an absorption coefficient of 0 means there's no effect whether there are scales or there are no scales. An absorption coefficient of +1 means all the sound is absorbed. And intermediately, there are these are absorption percentages. Negative absorption coefficient means the presence of scales makes the echo not weaker, but louder. So here, in this case, there is a 50% increase in the echo by the presence of the wing scales. The color code here is brown are moths, blue are butterflies. You can see structural differences on the wings, so they look very different, and they have a very different acoustic effect. And now this is the most amazing thing. So if you look at this curve, at the high frequency, it's not very good, but it gets really efficient at low frequencies. That's 50% sound absorption. Some of these go to 70%. You've got some that go up to 80% sound absorption at the lowest frequency we've measured. And that's something that electrifies any acoustic engineer. That's what they want. They want thin absorbers that that can absorb low frequency sound. So what we found in this study is that these moth scale layers are very thin. In other words, deep sub-wavelength broadband absorbers. Deep sub-wavelength means this wing thickness to wavelength ratio here that I've used as a frequency axis here. 1/10 means that that absorber can absorb sounds that have a wavelength that is 10 times longer than the thickness of the wing. Down here, it's 1/100. So from here to here, that's a factor of 10 in performance increase. And you can see that there is some of the moths reach this 1/100. We have done more measurements thins. We can go to 120, 130. That doesn't say anything unless you are an acoustics engineer and know that traditional absorbers fail below 1/10. So evolution has penetrated a space here that engineers can't. And they do this with the moth scale. So here you can see an individual scale. This is the best studied scale on the planet. We've done so much with it. So here that's the structure as we go through the top layer and then the bottom layer. So it has these longitudinal lamina. In the middle, it's hollow. It has nanoporosity. At the moment, I'm working on a grant by the BBSRC to study the evolution of its acoustic properties, but I can't really reveal what we are finding there at the moment. And the way they work in the sound absorption is by becoming resonators. So each of these scales has material properties, and when sound hits them, they start to vibrate. And we could find out from the nanostructure what the material properties are. And here, these are measurements, again, with this laser Doppler, which measures movement. So we send sound on it and look at whether it's vibrating. And we find these 3 frequencies in 3 different modes. So you can wave your hands in 3 different directions. So up and down, left and right, and rotation. And these are the 3 modes that we have here. And when we then model the same thing in a biophysics system called COMSOL, it finds the same modes, and it even finds them at exactly the same frequencies. So we got that, that's now 8 years ago, published. And that's the fundamental mechanism, how these wings become such powerful sound absorbers. So when these scales start to vibrate, that means the mechanical energy that's in air, that's what we call sound, is turned into mechanical energy inside the scale, vibration energy. And that means it's taken out of the air. It's no longer available to create echoes. this is a 3D model of what a moth wing, a Saturniid wing would look like. And you can see that the scales are not the same. There are many different sizes and shapes. And that's important because one scale only absorbs the frequencies that it's resonating at, but bats use loads of frequencies. So you want to have resonators at all the frequencies. So again, moth and butterfly comparison, if you look at the moth, this is the distribution of resonators on a defined patch of wing membrane. And you can see that all frequencies are covered by about the same number of resonators. That's in the upper surface of the wing and then the lower surface of the wing. And then we looked at the scales shapes, and we can then model which frequencies they should be resonating at. And these are box plots for each of the resonance modes for these scales. So we have an empirical observation of resonance frequencies, and we've got a theoretical explanation how it happens just by size and shape modifications. And if we compare this to a butterfly, we have some resonators at all frequencies, but most scales resonate at exactly the same frequency, both empirically and also in the model. And that means, and the reason for that is that the scales actually all look very similar in a butterfly. They're not nearly as diverse as on a moth wing. So we have got a mechanism here that the moth wing is an array of tuned resonators, finely tuned such that they cover all the frequencies that bats throw at them. And what really is amazing about this is the next step that evolution has taken. And that is it turned this as a field, an array of resonators that interact with each other. So they are inserted into the membrane. The membrane has some flexibility. And through that flexibility, they're coupled to each other. And what you can do is you can create in a model an array of 16 scales, and then you expand it mathematically in infinity and look at what the acoustic performance is. And that's what this plot is. So if I have a uniform resonator array with 45 kilohertz tuning frequency, 16 scales at the same frequency, that's the absorption we're getting. So we get some absorption at 45 kilohertz, and it drops off to either lower and higher frequencies. And if I change the frequency of that, you get the same shape moved up and down the frequency axis, exactly what we would like to see. But if we take the same 16 spots, but use one of these frequencies in a random pattern, we get a curve like the black curve here. Now, again, these are 16 scales in all of these curves, but the area under the black curve is so much bigger than the area under any of the colored curves. And that is because of this interaction. So we call this an emergent properties. So by putting them together in a certain arrangement, you're getting better sound absorption. And this is what turns this particular structure in an acoustic metamaterial. Acoustic metamaterial is something that has scales as unit cells. It gets ultra thin by resonant absorption, like I've shown you, and it gets broadband by a tuned array that interacts and gets this extra boost. This is the only known acoustic metamaterial ever found in nature. And I'm still fighting my battle with the engineers who think that they invented metamaterials and don't give nature credit for having done it first, like 60 million years ago. But I'm getting there. I think I've got a few of them converted. And the scales on the body, of course, is a porous absorber. And the scales on the wing are an exciting one because they're deep sub-wavelength and broadband, for which the engineers don't have a solution yet. And that might be part of why they don't like being outperformed by nature. So what we did is another study published in 2022, where we put a little metal disc, you can't see it here, a metal disc, and we put different versions of mothwing on top, also the same size and shape, either intact, shaved on one side, shaved on both sides. And now we've got a different measure. It's the reflection coefficient. In this way, low down the axis is good. And you can see that if it's intact, you get 25% reflection. So that's 75% of the sound does something else, is absorbed. And if you shave one, you only lose a bit of the performance. So now we are at 30% on average. So that's interesting. And we have now used that design principle in our attempts to do something with this discovery. So now we are talking technical applications. If you've ever been in a reverberation-free room or in shared offices, you see this technology often. You can see wall-mounted or ceiling-mounted sound absorbers, sound technology. And as I mentioned before, the thickness over wavelength ratio of these always is 1/10, not better than that. So high frequencies, we are very good at. Low frequencies, we fail. These are some of the best products that we have out there. This is the absorption coefficient. So these are technical absorbers. Here we've got 1/10. The broadband ones continue towards higher frequencies, just haven't plotted that. This is a resonant absorber that goes slightly below 1/10, but then the performance drops down quite substantially at lower frequencies. But that whole region here, that's the target region. Everybody wants to go there. Everybody wants to have solutions that can help control noise at much thinner footprints. And when we now look at our moths, I've already shown you that the T over lumbar is 1/100 or even better. So I've plotted a few examples. You can see that curve here that clearly penetrates that area. It's not perfect. We would like it to be even higher up there, but this is our challenge, and we've mastered some of that. So for the last 3 years, we have done a lot of work to produce something that we might, well, foolishly, I've called it sonic wallpaper once, and now everybody thinks about a blue hedgehog. So I'm calling it acoustic wallpaper since. And it's not even the latest design. Some of the designs that we have do this. You can see we are clearly in that region. And we continually develop new prototypes here. And so the acoustic wallpaper we're working on is up to 10 times, sometimes even more than that, thinner and lighter than existing products. We can make it modular. We can make it work for whatever frequency range you want to work it. And we've got loads of people that we are talking to for potential applications. Architectural retrofit is one. Homes like high-end audio fans or home office users who want to be in a better acoustic environment. Automotive and aerospace are very interested. And for example, cabin noise and appliances, engine noise, and of course there are defense applications. So we are talking to all these sectors, and we've got a company called Atticus Acoustics. So this brings us back to early in the talk. Atticus is the Atlas moth. So we've named our company after the moth species that has given us this fantastic invention. We actually haven't spun out. That is due in 7 weeks. We've got it patented. We are talking with all sorts of stakeholders about implementations of this. So from being a ivory tower ultrasound acoustician, I've now been turned into somebody who is trying to set up a business commercializing this fantastic discovery and that the humble moth has given us. And those of you who haven't seen it, I talked about this two and a half years ago, and somebody put it on TikTok and it went completely viral. So this little video, this 1 minute video, still holds the record for most views on TikTok for any higher education research content in the UK. So feel free to watch that. And at that, I think I'll end. Thank you for your attention.
Excellent, Mark. Thank you very much. Absolutely fascinating. Love the idea of Sonic the Hedgehog wallpaper. I'm sure lots of small children and possibly some bigger children would like that in their rooms. But yeah, fantastic stuff. So I'm going to I was going to say, if you have a question, and you can find a way to raise your hand, please do that. So for those of you who aren't familiar, that'll be in the React button. Where you find all the buttons, you hover over your screen. They're normally at the bottom, I think. You look at the React one, you'll find a ability to raise your hand. And we have some hands up already. So we'll go to Aidan and Emma with a hand up.
Right, thank you. Thank you. Oh, excellent and interesting, really interesting talk. I wanted to go back to your first example, which was the toxic moths that are producing a sound saying don't come and eat me. Two questions there. Firstly, how do you know which moths are toxic? And secondly, are there any examples of moths that are not toxic, which are producing sounds and pretending to be toxic, just as there are a lot of daytime insects which are yellow and black and pretending to be wasps?
Okay, this is a question asked like a true biologist here, so I'm suspecting you might have a background. So, first of all, the second part of the question: are there any cheaters? Are there any mimicry examples that are not true mimics? Yes, there are non-toxic species that produce this, like hoverflies mimic the wasp, so they just profit from that protection without giving back. Yeah. How do we know whether they're toxic? So you can do chemical analysis. You know these aromatic compounds that we find toxic. That's one way. The other way is some researchers in the Netherlands have fed Ipomoea to birds, and they throw up and get miserable. So that's another one, but it's very hard to get permission to do this. And the third way is you have an ambitious PhD student and he just tastes it.
Right. Lovely. Thank you very much.
That's great. Thanks very much. Yeah, that's old school natural history. That is just tasting things, isn't it? Right, Nick, you've got your hand up.
Well, first, I'm just thinking about the ethics committee issues for the tasting with the PhD student. Thanks, Mark. It was absolutely fascinating. That I don't know if this is a question or a sort of comment or just amusing. But my understanding was that bats actually have quite good eyesight at close range, and I wondered, therefore, as they come in and there's all this acoustic noise, why they're not just are they not able to switch to eyesight and say there's a nice body, or is it all just happening too fast? Maybe that's an unfair question of an acoustic engineer because it's about vision, but
yeah. So as an acoustician, of course, I don't find vision interesting. No, I'm joking. Of course, it's very interesting. This is a valid question. Many researchers have done cross-modal experiments, including myself. And the overwhelming answer is bats don't care about what they see.
So that eyesight is just to sort of
they use it for navigation. So what we know is they can see the moonlight, they can see the stars, they will see the horizon, the shapes. So they definitely use it to supplement navigation. But as far as prey detection goes, that's not the case. There is one interesting story, and that's an exception where we know by inference that bats can see the outline, and that's a moth. So cossets, oh God, what's the English name? So they swarm, where the males swarm just at the top of grass, and they do their little dance at dusk when the bats are most active, not later. And
one of the swift moths, like ghost
swift
moths.
Thank you for helping me out there. So the females sit down in the grass and do sexual selection, while the males do their little dance. And the approved theory there is that actually is entering. It's a real handicap principle. So they enter dangerous space. The higher they go, the more exposed they are to the bat attacks. And they do this at the time when bats get active over these meadows. And we know that the bats use echolocation, but the theory is that the bright white swift moth also signals visually to this predator. And if they can still survive, then they have the good genes. So I think this is one natural history story that sort of points at bats using vision in attack, but it's not proven. You have to talk to Jens Redell in Sweden. He's the guy who studied and discovered this.
Okay, thank you.
Great, thanks very much, Mark. I wondered, it's kind of following on a little bit from Aidan's kind of question about sort of cheating things in a way. It's not quite the same, but so you showed fascinating, clear differences between the scale structures on moth wings and butterfly wings. So that made me think, well, what about, so that's obviously about being day flying in butterflies versus nocturnal. But of course, in amongst our many conventional moth families, obviously butterflies are also moths, but there are day flying examples, and obviously there are some groups like the Zygenids that are all day flyers. So I wondered if you'd looked at the wing structures of those and whether they, whether they tell you something about when and how these wing structures evolved and what the real driving force is. Because one of the things I find really fascinating about all of the stories you've told is all of these structures are doing multiple things. You kind of gave the example of the snake's head on the wingtip and all of that. There's multiple stuff going on, multiple evolutionary forces happening on these structures.
Yeah, but so the question about how quickly they can switch from day flying to night flying is, well, I think that's the starting question. Multifunctionality is a big one.
Yeah. No, I'm sorry. I'm just going off on a tangent, really. Yeah. So what I'm wondering is, if you've got within a group of moths that are showing these adaptations in their wing scales, this acoustic cloak, if there's one or two species or genera that are predominantly day flying, do they not show those structures?
Yeah. So of course we've looked into this. So, and the group that I found most productive for this is the Uraniids, so tropical moths with many day flying taxa, and we couldn't find any effect there. So, and I think that's the most likely taxon to do this. So I have a feeling that all these super acoustic adaptations that we find are an invention, maybe an autapomorphy of mainly the silk moths, because they're deaf and they're big. And now the question is, maybe they have the ability to grow bigger because they're so well protected. We find functioning cloaks on all the native species. We've got, as you know, we've got some Saturniids in Europe, but the effectiveness is much lower in the UK species or in the European species than in the tropical Saturniids. That's one message there. So it seems like it's not that easy to invent this. So we are looking into this. Okay. So Richard, I've got a wife here who hasn't had her dinner, and she's actually asking me to see whether we can get to an end here. I don't know. I can't see many more questions at the moment.
No, I've not seen any other hands up, so that's fine. Let's draw it to a close. Sorry to have kept you and your wife from your dinner for so long.
My pleasure.
It's been a fantastic talk. There were some comments in the chat saying, thanking you for such a really fascinating, brilliant talk. So I will echo that on behalf of the whole group. Really, really fascinating stuff. So good luck with launching the company. That's obviously going to be a massive challenge and a lot of hard work, I'm sure. But we wish you great success with that. And if you let me know how you'd like people to contact you if they're interested in finding or recording moths to help you in your adventures in cataloging that sort of information, then let me know and I'll push that out to the group through our emails and newsletters.
Yes, absolutely. Do reach out by email.
Great.
Thanks a lot very much. It was a pleasure.
Okay, thank you. Bye.